Yeah. Am I audible to all of you?
Exactly.
All right. So I'll just start. Uh, right. So first, I will introduce myself. I'm Vijay Rane. I'm a Prime Minister Research Fellow in the IIT Delhi, and we are discussing the some problems based on the scores 1 and 2 dimensional spectroscopy for the chemist, and this course is taught by Professor N. Suryaprakash. He's from IIS Bangalore. Right. So in the second week, if you have covered the all the videos from the portal, so there will be a the first lecture was on the in it's about the resonance and the bulk magnetization. The second was on the signal detection and rotating frame concept. Later, pulse phase and signal phase, as well as the Fourier transform and the selection rule for the transition. So these are the some topic that we have covered already there. Also, I would like to ask you guys, do you guys facing any difficulty in the finding the uh, information regarding this topic online? You can tell me. I can provide some reference book if you want. So, or else, or if you have any doubt regarding this course, you can ask now.
Currently, you don't have any doubts.
All right. Yeah, since because it's like just starting, right? So I'll just yeah. So the course is only I mean in the initial stage. So all are like kind of informative type. So there will be not much any complicated. Just we need to see at least once the videos. Then you will get I mean know about the what are the topics that we are already covered in the first 2 weeks. So that if you don't have any doubt, we'll just discuss some problems. There was one question was asked in the last session regarding the gyrometric ratio. So this is the gyrometric ratio gamma, which is for the which is generally for each atomic species, and which is represented by the gamma, and which has a relation mu is equal to gamma multiplied by I. So here mu is the magnetic momentum and gamma as told earlier, which is like a gyrometric ratio, and I is the rotating spin. And here in the NMR spectroscopy, we generally deals all the property we are going to check for the nucleus. So here we are taking into consider I is equal to the relating spin of the nucleus. And there are multiple nucleus, like if you have hydrogen, helium, as well as the carbon 13, fluorine 19, sodium 23, or phosphorus 31. They have the different gyrometric ratio. And this gyrometric ratio decide the sensitivity of that nuclei to detect in the NMR instrument. So since if you look at here, so the hydrogen has the highest gyrometric ratio, which is about 42.58. The unit for this one is the megahertz per Tesla. So if you provide the 1 Tesla of the magnetic field, then at the time this will have the 42 megahertz frequency. So higher is the frequency, that higher the sensitive. It means the nuclei is highly sensitive to the magnetic field. So here, if you look at the fluorine, right here. So this fluorine also have some similar value to the hydrogen, right? So that's why the sensitivity for this one is like comparable to the hydrogen one. And if you look at the carbon, which has almost 4 times lower, right? Sorry, four multiple. The hydrogen has the four multiple higher gyrometric ratio. That's the reason. that time we have multiply by the 4 to calculate the frequency of hydrogen. There was some problem. I forgot the exact what are the exact problem, but yeah, we have multiplied by the factor 4. Yeah, and yeah, the sensitivity and Garmantic ratio. This is the relation. So larger is the the magnetic field, larger will be the energy, and the higher will be the sensitivity. So if you look at this one, the gamma, which is like directly related to this energy, so higher is the Garmantic ratio. That's why the it will give the nuclei will have the higher energy, and the sensitivity for that nuclei will be the higher. So that's why the hydrogen one nuclei has the higher sensitivity compared to all other nuclei. So this is also you can solve on the basis of you can also select the option which is in the quiz of the second week, right? So you can just use this concept. You will get you can easily select the which is correct answer. So higher is the Garmantic ratio. That nuclei will be the higher sensitive, and yeah. So again, there is another relation here as I told here. So hydrogen has the highest Garmantic ratio, right? So sensitivity higher among the all nuclei, stable nuclei. This is also one of the that we need to take. So probably the there is one question about third or fourth question in the quiz. So you can easily select the answer based on this one. Next one is the sensitivity depends on the multiple parameter, among which like the first one is the magnetic momentum. Second one is the population difference in the two energy states, and third is the coil magnetic flux or the provided magnetic field or magnetic flux. So all this factor depends on the Garmantic ratio. Thus, the sensitivity of the nuclei is like Garmantic ratio multiply the cube of the Garmantic ratio. So let's say if you take the example of if you compare if you do the comparison between the proton 30C and nitrogen. So let's compare between the proton and the 13C. So this is the Garmantic ratio. Let's take this one as a gamma for this proton, and which has this one for the carbon. So it will be 63. So 60 the 1H nuclei is 63 times higher sensitive than the 13C. Similarly, here also you can take the between the proton and the 15N. So it will be N15 has the negative magnetic momentum. So the value is it will be value of this one. It will be negative. And yeah, we can see here the 1H is 63 times more sensitive than the 13C, and 960 times more sensitive than the 15N nuclei. The another one is the sensitivity also depends on the natural abundance of that isotope. So let's take we have the 1H proton, which is like presented in 99.98% in the all. So let's take example of the benzene, and it has the 6 hydrogen. So and if you take the multiple, take the solution of the benzene one. So among that, like among the 100%, there'll be if you focus on this hydrogen particularly. So among the 100, there will be only 1% will be the deuterium or the deuterium plus uh, another isotope deuterium, right? So which is like they both are presented only 1%, and this NMR active nuclear 1H, so which is like 99.90%. So it indicate this hydrogen will have the very high natural abundance. But if you compare other nuclei, so let's take example of 13C, which is only present in the 1.1%. remaining is 12C, right? So other are, but among this C12 is not NMR active. Only 13C is NMR active, and which is present in only 1.1%. So that's the reason if we do the NMR spectra of this 1H and 13C. So if you have some compound, if you want to do the NMR spectra, so the proton will take only 2 to 3 minutes. But for the same one, this 13C will took about 20 to 30 minutes for the same sample. So because of this natural abundance of the 13C is very low. Another example of the very low natural abundance is the nitrogen 15. So which has natural abundance like 0.37%, which is even less than the 13C. So that's why if you want to take any NMR of this nitrogen 15, it will took hours maybe, or more than, definitely more than hours. Similar for the oxygen, which is like 0.037, again lower than this nitrogen. So these are only the NMR active nuclei in the oxygen 17. And generally we have the more abundant nuclei of the oxygen isotope will be oxygen 16, but NMR active only this one. So that's the reason we don't generally do the oxygen 17 as well as the nitrogen 15 NMR, because it took too much time. And yeah, here also mentioned like among the 100 molecules contained in single carbon NMR active, and 99 are they contain the carbon 12 which are NMR inactive. So this type of nuclei are very much insensitive to the NMR, but the proton one is very highly sensitive to the NMR instrument. So that's the reason we get the NMR spectra within a 1 or 2 minutes. And also we don't require to do multiple scan. But if you do the if you see the carbon, we generally do the too much scan, like uh, more than 100 or sometimes 1,000 scan also required for to get the good carbon spectra. But for NMR spectra, we only do the 4 to 8 scan, or maybe sometime if if you have the sample very dilute, then we need to take 16 scan. But it generally takes within 2 or 3 minutes you can get the proton spectra. Also here some uh, resonance frequency in megahertz of these different nuclei in different magnetic fields it is given. So let's take the one as a base one. So if you look at here, which is exactly 4 times lower for the carbon, right? So if you have some instrument which is like 3, 4, 500 megahertz NMR instrument, so that will show for the hydrogen it will be 500 hertz only, but for hydrogen, but for 13C it will be only 125 megahertz because of this one. And again, similarly for the other also, it will be a comparative. This is the table that you can find in the first or second week content in the lectures. So it shows the nuclear spin uh, as well as the which are the NMR active nuclei. So the hydrogen has the nuclear spin. This red color indicate 1/2, which has the nuclear spin half. The yellow color, which indicate the 3/2. This yellow color will indicate the 3/2. Later, the green color one, which is indicate the 5/2. So in this way, the nuclear spin of the different nuclei is given in this table. You can have a look. So it might be helpful for your, I mean, if someone preparing for some examination, it will be good for them. All right. So, so if you don't have any doubt, we'll see some problems based on the topic that we have covered in the first week, right? And we are not going to solve all the problem. We're going to just discuss the problems. I will not tell you the exact answer here. So you have to tell me the what are the answers according to you. So the first question is, Under thermal equilibrium, with the random phase approximation, the bulk magnetization M0 is measured to be. So it is given here. So you need to tell the exact answer for this one. So what are, sorry, this one will be the D. This is A, this is B, this is C, and this is D. So which answer is the correct here? So anyone have any answer here? All right, I have seen the chat. Someone told I am not audible. So all right, I will increase my volume slightly. So all right, in the first question, the question is under thermal equilibrium with random phase approximation, the bulk magnetization M0 is measured to be. The first option is aligned with external magnetic field and oscillate at the Larmor frequency. The second option is the aligned in the direction perpendicular to the external magnetic field and is oscillating. The third option is it has the magnetization component randomly distributed. And fourth option is aligned with the external magnetic field. Uh, Also, it will be a static, and mz is not equal to 0. Mx is equal to my, which is equal to 0. So here, it will be. I will tell you the first option because it looks somewhat complicated question. Option D is the correct option here. It will be the under thermal equilibrium, the random phase approximation. The bulk magnetization M0 is assumed to be aligned with the external magnetic field, and mz is not equal to 0, as well as the mx and my uh, will be the 0 here because it is aligned, right? That's why along the x-axis it will be a non-zero, but along the uh, x and y it will be a 0. The next one is the 1h and 29 SI have the positive and negative magnetic momentum respectively. In a magnetic field of 14.10 Tesla, the protons precess at 600 megahertz. Then which of the following statement is correct here? So anyone have any answer here? You can also paste in the comment section if you know any answer here. Does anyone here? I will tell you this answer for this one as well. So let's we have the 1H, right? Which resides at the frequency of 600 megahertz. So which of the following statement is correct here? So here both 1H and SI species at the same frequency and their direction of precision are same. The second option is the 1H precedes at 600 megahertz and SI precedes at the 19.23 megahertz and their direction of precision are same. The third, both 1H and SI, uh, they precede at the same frequency. and the direction of precision are opposite. The D option is, sorry, fourth option is the one is precise at the 600 megahertz and SI 29 which precise at the frequency of 19.23 megahertz, and the direction of precision are opposite. So here I would like to mention the direction of precision will be the remain same. Only unit, yeah, here it is. The option B is the correct option here. The direction of precision will not gonna change, but only thing you need to check using this the initial as like we can calculated for this one. Here also we can, do we have here any silicon? No, here it is not mentioned actual exact frequency of this silicon. Anyway, it is not mentioned, but only there are two values that we need to, but in the both cases, they are the same values mentioned. So obviously, among these two, there will be the correct option. But also, you need to check here. It will be the same or opposite. It should be the not opposite. It should be the same one. This option is the correct option here. And if you have given any time like different nuclei, uh, rather than the silicon or this one like carbon, then based on the initial that problem that we have solved in the last week, uh, as like the proton, I mean the correlation between proton and carbon, you also need to do the correlation between proton and silicon in the same manner here as well. The next question is the population ratio between the two energy states depends on. So what are the factor that on which the population ratio between two energy states will depend? We have different energy states. Let's say this was the lower state and this excited state, and we have some population here and some here. So what are the factors which affect this population? So anyone have any idea what are the to be the correct option? So the first option given is the external magnetic field B0. The second one given is the temperature. Third is not depends on either temperature and magnetic field. And fourth is the depends on the external magnetic field V0 and the temperature T. So what do you think which option is the correct here? Someone commented option D. All right. Yeah. Option D is the correct option because this one, the energy, the population between two energy state. If you increase the temperature, then the population in the higher excited state will be increased. This population increase with temperature, directly related to temperature. Also, if you increase the external magnetic field, that time also the this population is increases. So if you increase the uh, temperature, the population in the higher excited state is going to increase. Also, if you increase the external magnetic field, that time also the population in the excited state will increase. All right, this is the another question, and the question says the three spin one half nuclei are interacting. So we have three nuclei which has the spin one by two. The possible magnetic quantum numbers of the eight energy states are. So we have the eight energy state. If you have three nuclei, the spin they have uh, one by two. So the possible magnetic quantum numbers of the eight energy states are. So you need to calculate this one. So what are the possible magnetic quantum number for these three nuclei? So which option here correct one here? You can put into comment. So here option for this one is the option A is the correct option. So if you have the different number of n states, Yeah, option A is the correct option here. Because uh, this will be the, sorry, it will be minus 3 by 2. Yeah, minus 3 by 2, minus 1 by 2, minus 1 by 2, minus 1 by 2. Again, the similar manner, it will be equivalent from here. Plus 1 by 2, plus 1 by 2, plus 1 by 2, and 3 by 2. So these are the 8 possible magnetic quantum numbers for this nuclei. The another question will be the question is the in the rotating frame when the spins are at on resonance, which of the following statement is true? Spins are at on resonance. This point you need to highlight. I want to highlight. So which of the following statements are correct? The first option is the effect of external magnetic field. The B0 stands for external magnetic field as seen earlier. The external magnetic field will be disappear. Sorry, it's not the right one. External magnetic field will be disappear. The second option is the B1 field is static. That is, it will remain same. The third option is the rotating frame coincide with the laboratory frame. And fourth one is the magnetization precise around the B0. All right. So which option here correct one? Any anyone have any idea here? Which option is correct here? Also, you need to I like to mention in this statement which statements are true. It may be multiple. So you can have multiple. This is called a multiple selective question. So you can select multiple options as well. All right. So here the first option it will be disappears because it is resonating is in the on resonance, and another one is uh the B1 it will be the static. So the external magnetic field will be disappear, and the magnetic field that we can the B1 will be the will remain same or the static. So the option uh one and sorry A and B sorry 1 and 2 are the correct option here. So these are some question. It's like same from similar from the assignment or maybe same from the assignment one. And since it is like we are just started the course, the all the questions will be theoretical. So it's like some kind of informative question. So there will be no any calculation or that type of questions, or there will no any problem based on this question. So does anyone have any doubt regarding the anything that course uh, or any topic that you have that covered by the professor in the first and second session? You can let me know right now, or you can also use there is Q&A session. So uh, anyone from the assigned TA, they can also I mean answer your query there itself in the mail. So anyone have any doubt here? All right, if you don't have any doubt, then I think we'll stop here for today. I will just stop the recording.